All right, let's take a look at another example, maybe a little less serious one. So suppose every week you go to buy bagels. There are these two bagel shops that you've been going to, and of course, as one is prone to do, you get home and you measure, you weigh your bagels every time you do them, just to see how much bagel you're getting, right? And you find that over many years of observations that in bagel shop number one, and in both bagel shops, the weights of the bagels are normally distributed. Um, but they're more consistent in the first shop. There's a standard deviation of 12 grams in the first shop, whereas there's a standard deviation of 30 grams in the second shop. Okay, so now so a friend comes over and you're trying to explain how you've noticed this over the years, that the weight is more consistent in one shop than the other. And so what do? You go out, you buy a dozen bagels from each shop, and you're like, look, I'm going to show you the standard deviation in one of these bags is going to be like twice as big as the standard deviation in the other bag. What's the probability that your demonstration will actually be successful? So you know over the long term that overall the standard deviation in one shop is 12 and the other is 30, so more than twice. But with a given sample of a dozen bagels from each shop, is that going to hold through? What's the chance that actually your standard deviations will be twice as big, at least in one shop, than the other? So let's let S1 be the sample standard deviation for store number one. Now, recall we're getting a dozen bagels from each store, so here we have N1 is equal to 12. And S2 is going to be the sample from store number 2. Here N2 is going to be 12 as well. And of course, we know that the actual population standard deviation for the first store is 12, and the actual population standard deviation for the second one is 30. And we're interested in the probability that if we take a sample from the first store, the standard deviation from the first store, and sample standard deviation from the second store divided by the first store, we want to know, is this at least 2? Is the standard deviation from our sample of a dozen from the first store going to be at least twice as big as from the first store? Okay. Well, what do we know? We know that some combination of these give us an F random variable. So to get our F variable, we have to look at S1 squared divided by sigma 1 squared divided by S2 squared divided by sigma 2 squared. This is going to be an F variable. I'll call this F, and it'll be an F variable with 11 and 11 degrees of freedom. 11 because 12 minus 1. We'll be able to look that up in a chart then. Now, of course, we actually know these sigmas, so this is actually equal to S1 squared over S2 squared times the ratio of the sigma squareds. So this is, what is it? Sigma 2 goes on the top after I flip this around, 30 over 12 quantity squared. Okay, so in other words, it is so S1 over S2 quantity squared. 30 over 12, that's 15 over 6, that's 5 over 2, and I'm squaring that, that's 25 fourths. Okay, so we got that that's our F variable. So we would like to translate this original issue with the probabilities in terms of this F variable. So we find that this is the same as the probability. Let me flip my guy over just for convenience. Reverse the direction of the inequality. And this is, then I'll square both sides. So I got S1 over S2 quantity squared is less than or equal to 1/4. And now I'm going to multiply by 25 fourths. Less than or equal to 25 fourths times 1/4. Okay, and so I'm interested in the probability that my F random variable is no more than 25/16. Okay, and that is the probability that our demonstration with our friend will be successful. So let's just go ahead and calculate that by sticking it into R. Okay, so looking into R, let's say, hello R, please help us. We want the probability function, the cumulative distribution function going up to 25/16 for 1111. And it tells us that 76% of the distribution roughly is between 0 and 25/16, which tells us that there is a 76% chance roughly of our experiment being successful. So this is about 76%. So this is the chance of a successful demonstration. All right.